Hello everybody. Ever since man began populating the earth, he was driven by a force to unfold the concealed and explore the unexplored. In particular, he was very eager to familiarize himself with his immediate surroundings, the place he lives, what are all in it, etc. And this knowledge was very crucial for his survival. Subsequently, it led him to document his findings for successive generations to benefit from it. In this video, we will discuss the various methods used to measure and record the various details found on the Earth's surface. If you feel my video has enlightened you, then why hesitate to hit the like button? Everybody likes stories, and I will start with one. A school-going boy, we will call him Galvin, okay, was once kidnapped by some bad men and is locked up in an abandoned house outside of town. One fine morning, while the kidnappers were away, the boy managed to escape from the house. As he runs along the road, he comes across many things, or what we call landmarks. Okay, what all did he see? First, he comes across a pond and cows grazing nearby. Then he sees a tree house. Suddenly, he encounters one of his kidnappers themselves. Scared, he hid behind a tree. Feeling very tired after such encounters, he takes a nap under a big tree. His urge to escape and reach for help made him run again. He comes across a beautiful temple followed by a hospital. Accidentally, he stumbles across a policewoman. Now he can confide in them all that he had undergone, eventually leading them, that is the police, to his kidnappers. Before that, he first needs to organize his thoughts and the various landmarks he had come across in a sequential order. Secondly, he needs to place those landmarks in a spatial perspective. That is, what he saw, where he saw, and so on. In order to do so, he uses some drawings, words, and symbols or numbers. For instance, if this is what Galvin gave the police, then, by the way, can you make anything out of it? If not, then continue watching. First, we will draw a grid. The columns, we name them A, B, C, D, and the rows, we name them 1, 2, 3, 4, 5. We then place those landmarks in their respective places. The hospital we place at 1B, the temple at 2C, the bushy tree at 2A, and like this we place the other landmarks too at their proper places. Now we see a detailed picture that will eventually lead the police to the whereabouts of Galvin's kidnappers. This Galvin's ability to express what he sees through the use of pictures, words and symbols is referred to as mapping skills. Welcome to my channel. This is the social teacher joining you in this endeavor. The objective of watching this video is to enable viewers to understand the various components of maps, the methods of surveying, aerial photography, remote sensing, GNSS, GIS, etc. Map as a tool. A map is a very essential tool with a geographer. It is worth 1,000 words, and mapping skills are the basics to understand a map. Maps are also used by many other people for very many purposes. It is an illustration of the Earth's surface through the use of pictures, words, and symbols. Thus, maps can be defined as a drawing of an area as seen from above. It is a basic tool of a geographer. And thirdly, it is a location guide. That is, it can show which is where and so on. Oh, is it lunchtime? What do we usually have for lunch? Usually we have rice, sambar, appalam, poriyal, etc. for lunch. All these several dishes put together, we call it a meal, isn't it? So also a map too encompasses several components within it. They are the title, scale, direction, grid system, projection, legend, conventional signs and symbols. First, the title. A title indicates the purpose or theme for which a map is drawn. Here, for example, this map shows the major rivers and dams found in India. The second component in a map is the scale. We've already seen that a map is a diminutive image of the Earth's surface, or in other words, a representation of the Earth's surface in a miniature or reduced scale. And it is the scale that makes it possible for us to reduce or shrink the size in such a way that it could be precisely duplicated into a small sheet of paper. Thus, scale can be defined as a ratio between the actual distance on the map to the actual distance on the ground. Let's take the example of two places. If the actual distance between Selvapuram and Singanallur is 10 kilometers, then on a map of Coimbatore, they could be drawn with a distance of 10 centimeters apart, such that every centimeter on the map represents 1 kilometer on the ground. And when the scale is written as 1 centimeter is equal to 1 kilometer in a statement form, then it is called the statement method. Another method of representing a scale is the representative fraction method, or shortly the RF method. It describes the proportion or ratio of the distance on the map to the actual distance on the ground. It could be stated as 1 by 1 lakh or 1 is to 1 lakh. This means that 1 unit on the map represents 1 lakh units on the ground. And those units may be either in an inch or a centimeter or any other standard measurement. The third and last method is the linear or graphical scale method. In this method, a divider is used to find the accurate measurement between these two places. And for an approximate measurement, the first two fingers are used. This linear or graphical scale method is very suitable for large scale maps. This linear scale is a straight line whose length is divided into equal proportions or parts, and each part will denote that much distance on the ground. Next is the direction. Maps are normally drawn with north orientation. Naturally, the north direction in a map is always towards the north pole of the earth. And it is usually indicated on a map by a north-south line with an arrowhead on the north side of the line. The next component in a map is the grid system. We are all well aware about latitudes and longitudes, aren't we? These imaginary lines drawn across the length and breadth of a map is referred to as the grid system. These latitudes and longitudes help us to find the location of a place. In normal practice, the latitudes are stated first and then the longitudes are written. They are expressed in units of degree, minutes and seconds. Next is the projection. Map projection is a way of showing the spherical shaped earth onto a flat piece of paper. Imagine a clear spherical ball with a light bulb inside it. Suppose we draw the latitudes and longitudes over it and project it onto a paper. The image of the grid will be reflected onto the paper. And if we stick a transparent map on the glass globe, the outlines of the land masses would naturally be reflected on the paper. Thus, map projection can be defined as the transformation of the spherical network of latitudes and longitudes onto a plane surface or a flat surface. Projections are drawn to maintain the exact shape, area and directions of the Earth's surface. Some three methods are widely used in projections, and they are projection on the surface of a cylinder, projection on the surface of a cone, projection directly onto a flat plane also called planar or zenithal or azimuth projection. First, how is projection on the surface of a cylinder done? Here, a transparent globe is placed inside a cylinder and its contents, when imprinted onto the cylinder and rolled out into a flat plane, we get this cylindrical projection. In this projection, the entire world is represented in 360-degree panoramic view. The next type is the projection on the surface of a cone. This is done by placing a cone over the illuminated transparent globe. As the projected light from the globe falls onto the cone, the outlines are manually drawn by hand. In this type of maps, the longitudes are drawn in straight lines, whereas the latitudes come in concentric circles. In the third type, projection is done directly onto a flat plane and it is called planar or zenithal. Also called the azimuthal projection, they are used to project the Earth onto a flat surface. These projections are drawn with a view to better accommodate the polar regions, as usually these polar regions are not given much prominence in rectangular maps. And so, with a view to give better prominence to it, the United Nations organizations has incorporated this projection in its emblem. Legend. Also called a key, it is either placed at the left or right bottom corner of the map. A legend helps to understand the various signs, symbols and colors used in the map. Conventional signs and symbols. In maps, universally accepted signs and symbols are employed to represent certain features in maps. They may be physical or cultural features. Of the three types of symbols used in maps, the first is the point symbol. They depict features like buildings, cultural structures, trigonometrical beacons, etc. The next are the line symbols. They represent the railways, roadways, power lines, waterways, etc. Area symbols. Cultivated lands, ponds, orchards, water bodies, etc. are represented with the help of these symbols. Some of the conventional signs and symbols used in maps are shown here. Next, color codes. Various color codes are used in maps to differentiate the various features such as water, land, vegetation, etc. The following color codes are used along with map symbols. The color brown is used to denote land or earth features such as mountains, contour lines, etc. The color light blue is used to denote water features such as rivers, lakes, etc. Dark blue on a map typically represents deep waters such as oceans, national waterways, etc. The color green generally represents vegetation features such as cultivated fields, woodlands, natural vegetation, etc. Black color is used in maps to show construction features such as roads, railways, bridges, telephone lines, boundaries, etc. Similar to the black color, red is also used to show construction features but on a greater scale, such as national roads, major roads, lighthouses, state boundaries, airports, names of cities, places, etc. The color pink is used to denote international boundaries. In this map, the legend clearly shows the several colors denoting the various features seen in an area. These color signs and symbols are usually drawn only after making a thorough examination and measuring of the target area. This art of measuring the Earth's surface is called surveying. In order to accomplish this, geographers use several instruments such as the chain, prismatic compass, plane table, dumpy level, ebony level, clinometer, theodolite, total station and GNSS. Chain. Also called the Gunter's chain, it is a distance measuring device used in surveying. Clinometer. It is used to measure angles, heights and slope of buildings, towers, mountains, etc. Okay, I will show you a do-it-yourself model of a clinometer. All you need is a protractor, a hollow tube and a pendulum. Called the Indian clinometer, we can do it ourselves. And by using this formula, we can easily determine the height of a building or mountain, etc. Next is the prismatic compass. A compass is a device that shows the cardinal directions, that is the north, south, east and west. It has a magnetized needle inside it, which makes it to constantly align itself with the Earth's North Pole. It is extensively used for navigation and geographic orientation. As maps are normally drawn with north orientation, a compass remains an important tool in surveying. The theodolite. It is a precision optical instrument for measuring the angles between designated visible points in the horizontal as well as vertical planes. Traditionally, it was used in land surveying. It is also extensively used for building and infrastructure construction and some specialized applications such as meteorology, rocket launching, etc. Total station. It is a modern surveying instrument that integrates an electronic theodolite with an electronic distance meter. It is a multi-purpose surveying instrument. GNSS or Global Navigation Satellite System. It is a method of surveying with the aid of a GPS or satellites. And it encompasses all the navigation systems using satellite signals to calculate the position of a receiver. Basically, it involves a base station, one or more rovers or satellites to receive GNSS signals. The base station receives signals from satellites and transmits the data to the rovers, allowing them to compute precise coordinates or location of an object or receiver. Next, we will move on to maps. In general, maps are classified into large-scale maps and small-scale maps, and they are drawn after surveying a target area. When a small area is shown in an enlarged scale, such as the one you see here, it is called a large-scale map. Whereas a large area, when shown in a miniature size or a reduced format, it is called a small-scale map. Till now, we were seeing some methods of surveying or measuring Earth's surface from the ground. In the middle of the 19th century, people started doing the same measuring remotely. That is, they did the surveying not on the ground but away from the surface, as it provided better and precise measurements. Well, I will explain it for you. We have the eyes, nose, ears in our body. The eyes help us see an object. With the nose, we are able to smell it. The ears help us hear the noise that comes from the object. This appearance, smell and noise from an object we get to know through these three sense organs. The point is, these sense organs are doing this job without actually coming into contact with the object. This characteristics of these three sense organs is a good example of remote sensing. Thus, remote sensing can be defined as observing and measuring earthly objects without touching them. And today, remote sensing has become the chief source of map data. Remote sensing has a long history dating back to the 18th and 19th centuries, where cameras were mounted on balloons and pigeons to take photographs. During the 20th century, airborne photographs and satellite remote sensing took aerial photography to the next level. Aerial photography. It refers to the technique of obtaining information about places or objects with the help of photographs taken using cameras mounted on low-flying birds, balloons, helicopters and aeroplanes. Flying at a predetermined height and speed, aircrafts take photographs with a time gap of say 10 to 30 seconds. As these photographs are taken while in motion with a specific time gap, they normally overlap with one another. That is, a part of the area that is found in a photograph will be found in the next photograph also. And the percentage of overlap will depend upon the speed of the aeroplane and the specified time interval. When the aeroplane flies at a higher speed and takes photos at a shorter time gap, the overlap tends to be greater, and vice versa when it flies at low speed and longer time interval. This type of overlapping is called a forward overlap. When the next flight moves in to photograph the next or subsequent study area, here too overlapping occurs. Here overlapping will be about 20 to 40%, and this type of overlapping is called a lateral overlap. These photos or mosaics we call it will be manually aligned by carefully clipping away the overlapping areas. And the various photos will be put together to create a composite image of the study area. This will then be combined to form a stereoscopic 3D image of the study area. Okay, photographs that are taken by aeroplanes and drones, we can easily get them as soon as the aeroplane touches the ground. With satellites, how do satellites take photos and how do we get those images? How do satellites help in remote sensing? Satellite remote sensing is the science of collecting data about an object or area from artificial satellites orbiting the Earth. Components of remote sensing. We've already seen that aeroplanes, drones and satellites take images of the Earth. Equipments installed in those flying objects to take the photographs are called the sensors. And with the help of those sensors, they take images of the whole Earth or part of it. The area that is photographed is called the target or the target area. Here there is something. Are you able to see them? No, you need some light, okay? Maybe a torchlight might help to illuminate those objects, isn't it? So also, for that reason, the cameras that we use has flashlights to illuminate the objects that need to be photographed. But how could a satellite placed so high in space illuminate the objects to be photographed? Well, they don't use flashlights. Actually, Earth observation and reconnaissance satellites that are usually placed in low Earth orbit between 160 and 2000 kilometers above the Earth uses the sun's rays to take photographs. So, photographs are taken only during the day. And so, the sun becomes a major component of remote sensing. The reflected sunlight from the target is captured by cameras placed in the satellite. And so images are always photographed during the day. And the signals are then sent back to a ground station on the Earth in the form of radio waves. The signals are then sent to a processor which manipulates the ones and zeros for digital mapping. Ones and zeros. I can give you a broad outline of how computers create 2D images. A processor is one big computer, and we very well know that they work on binary digits or bits. Bits are the smallest piece of information a computer can store. We will group the zeros and ones into separate groups. These bits the computer has animated like this. The vegetation, that is trees, etc., since they reflect less light, they are assigned ones. And since the water bodies reflect more light, they are assigned zeros. That's how the processor creates virtual images. With the advancement in space technology, high-resolution infrared cameras in satellites use the heat emitted by objects on the Earth, or by using the moonlight, etc. They can detect objects even at night. Have you ever booked a cab using a smartphone app? Did you see the map showing the route of your travel and the movement of your vehicle on mobile phones? How is it possible to calculate the time duration of your travel? It's the GNSS, the acronym for Global Navigation Satellite System. Though not very popular when compared with the GPS, actually the GPS is just an example of GNSS technology. It consists of three segments. The space segment, it sends signals to the control segment, which then sends the same to the user segment, thus helping us to locate, monitor and track a user's vehicle anywhere in the world. Usually, a group of satellites, say 4 satellites to be precise, work in tandem to pinpoint the exact location, speed and time of the receiver. However, some phones called satellite phones have direct satellite connectivity, which allows them to send signals to satellites orbiting above the Earth. Some examples of GNSS are USA's Navstar, or the Global Positioning System (GPS), Russia's GLONASS, Europe's Galileo and China's Beidou. India's IRNSS is still in the developmental stage. We will take the example of USA's Global Positioning System, or the GPS. It is a constellation of 24 satellites orbiting the Earth in 6 different orbits at 20,350 kilometers from the Earth. Some 4 satellites in each orbit provide real-time data to its users. Established by the US Department of Defense, it became fully operational in 1995. GPS receivers are installed in ships, planes, trucks and cars, cell phones, etc. Besides being used in providing location, direction, speed, etc., GPS also helps in weather forecasts, earthquake monitoring and environmental protection. Who puts those satellites into space? It's the rockets that place those satellites into space in their respective orbits. Satellites carrying rockets usually have three stages. The first two stages form the propulsion rockets. You could actually see the nozzle of the second stage rocket seated inside the first stage. The third stage consists of the satellite casing, inside which is the actual satellite itself, with its own rockets. Besides these, multiple strap-on booster rockets will be attached to the first stage. And these boosters are strapped on chiefly to provide the necessary thrust to counter the immense gravitational pull of the Earth. After liftoff, the first stage rocket, along with the strap-on booster rockets, takes the satellite to the edge of the atmosphere. And by the time the fuel is spent, the strap-on booster rockets, followed by the first stage rocket, will disintegrate and fall back to the Earth. The second stage rocket will take the satellite further into space. The third stage rocket will help position the satellite at the predetermined orbit. Next is the Geographic Information System called the GIS. Look at this picture. The pencils are scrambled, isn't it? Shall we organize them in a systematic order? And this GIS is actually a computer-based tool designed for managing a large amount of data in a systematic and affordable manner, collected for a given geographic region through remote sensing. Here is another example. In a given geographic region, let's see how many houses are there. How many recreational facilities? Is there sufficient green cover, that is number of trees in that area? Instead of manually visiting the place in person and gathering the data, remote sensing, that is satellite imagery, is used to gather the required data. Each type of data is then stored on a separate layer of the map. Depending upon the requirement, these layers can be added or removed. By this, the computer can create a map showing a combination of, say for example, hospitals, schools, recreational parks, ATMs, etc. for the intended purpose. So, GIS is a combination of computer software, hardware, geographic data, and the personnel. The key ingredient is of course the location. For that, we need to have a coordinate, an address or a distance from a known point that helps us to link the information to a location on the map. So, in short, GIS refers to arranging the various facts on a particular area in order. And this potential of the GIS was first recognized in the late 1950s by Waldo Tabler and Roger Tomlinson of Canada, who started importing GIS for public welfare. And since then, Google Earth have been the chief source for GIS images. Today, GNSS is widely used in fields of agriculture, emergency, survey, navigation, etc. So, in short, GNSS refers to a group of satellites that provide answers to questions such as where am I going, how should I go, what time will it take, etc. As with any development, this space technology too has its own drawbacks. Look at this image taken by NASA. Look at the quantity of junk flying in our space. Are we not responsible for this? The possibility of space trash falling on the Earth and causing damage is imminent. Thank you.